Right, so I'm sure you're all aware with the story of Newton sitting under the tree and an apple falling on his head. And like it says there, millions saw the apple fall, but Newton was the only one who asked why. Whether or not that actually was the event that led to Newton forming the equation that we're going to see in this section, it doesn't matter, because the equation holds true for an apple falling on anyone's head. Anyone's head? Maybe not anyone's head. Unless you have the force, perhaps you too could, like Yoda, have moved the apple away from your head. But we're going to be sticking with gravity and not the force that Yoda possesses, my young Padawans. Right, so today this video is all about Newton's law of gravitation and gravitational field strength. By the end of the video, you need to have a solid understanding around those couple of topics. The application skills, that is what we will be applying these understandings and practicing these skills in the lessons to follow, which is why it's really important that you actually watch this video. Just make sure you should all be have Moodle open right now. Make sure you can download this PowerPoint and download the fat animation that goes with this, the gravitational field strength. It's on Moodle, so make sure you do that before you carry on. Right. Let's move on. So let's have a closer look at Newton's law of gravitation. Right, so what variables should we consider regarding the falling apple and Newton? So that's what I want you to think about. And unfortunately, my animation there isn't working, but we're going to continue. Think about it. You should be thinking things along the line of, and fill in the blanks. I hope you're doing that. Let me give you a minute. Okay, so hopefully you would have got things like the masses of the objects and the distances between the two objects. Alright, so Newton proposed the attractive force of gravitation between two point masses. Note the word point highlighted. Examiners want you to say that, so say it. And he came up with this formula that the forces between two objects is directly proportional to the products of the masses of the two objects and inversely proportional to the squared distance between them. And this is universal, all right? Meaning that any two objects in the universe, even Yoda and you right now, have an attractive force between you. The equation in yellow there has a constant g, which was later found by Cavendish, who conducted his famous Cavendish experiment and actually calculated the value of g. And this is what he did. So this is Cavendish's experiment, and it's what he did to find the actual value of big G. And I think if Stephen Hawking were a woman, this is what she would sound like.
In 1798, Englishman Henry Cavendish used equipment similar to the apparatus shown to measure the gravitational force between two objects. The apparatus had a horizontal rod with two small lead spheres attached to each end. The rod was suspended at its midpoint by a thin wire so that it could rotate. Suspension by a thin wire meant that the rod and spheres were very sensitive to horizontal forces. To measure G, Cavendish placed two large lead spheres in a fixed position, close to each of the two small spheres. The force of attraction between the large and the small spheres caused the rod to rotate. When the wire's resistance to twisting equaled the gravitational force between the spheres, the rod stopped rotating. By measuring the angle through which the rod turned, Cavendish was able to calculate the attractive force between the objects. By substituting his experiment's values into Newton's law of universal gravitation, Cavendish calculated an experimental value for G.
Now let's have a quick look at this video from a clever guy.
One of my favourite scientists. is Henry Cavendish. Even though he was part of the rich dukes of Devonshire, that family, and incredibly rich, he went to Cambridge to study natural sciences, or natural philosophy as it's called. But he had a very curious condition in that he could hardly talk to anybody. So when it came to his Viva exam after 3 years of study, he fled Cambridge rather than sit in front of the examiners because he was petrified of them. But he was one of the most brilliant scientists of that 18th century in both chemistry and physics. For chemistry, he's noted because he analysed gases in the air. He discovered there was hydrogen, which is a huge component of the universe. He called it inflammable air. So he put some acids in a container, dropped some metal like zinc into hydrochloric acid, and got the gas to come off. And then to show us it was inflammable, you could set light to it. He breathed it in and blew it into a candle. Now, do not do this at home because it blew up and took all the hairs off his face. He invented the idea of electric potential before everybody else and used to set electric currents through his body to work out the voltage is proportional to current, and he measured the current by the degree of agony he felt with the electrical current. This is not the normal sort of person. He couldn't talk to most people. He couldn't talk to women at all. His housekeeper would get a recipe for something or other, and he'd say, no, lamb tonight, leg of lamb, and leave a note for her. He wouldn't say it, he'd write it. He would dine in the evening with his friends, and he would talk to them, but if he didn't know somebody, and you wanted to ask him a question, apparently you had to go to the Royal Society and he'd be in the room and you'd address the room this question about physics and you postulate, and if he felt in the mood he would reply to the room. He was a very strange man, and yet he's absolutely wonderful. He invented hydrogen. People went up in hydrogen balloons and could see the world from through that perspective. He did most of the experiments quietly on his own, keeping his notebooks, and it was only after his death and a persuasive campaign by Clerk Maxwell, the famous Maxwell of Maxwell's equations from Cambridge University, that he actually got the notebooks from the estate of the Dukes of Devonshire and discovered after the event that Cavendish had discovered the unit of capacitance, discovered dielectric constants, he discovered Dalton's law of partial pressures, he discovered or written about Coulomb's law, all before these guys had done it, and just left it unpublished in his notebooks. Towards the end of his life, he did a crucial experiment, which is represented by these lead balls. He lived in Clapham Common, which is nowadays a very poor part of London, but there it was quite fashionable, and he built his own place. His library he built somewhere else because he didn't want anybody borrowing his books from his house. Otherwise, he would have to ask the book back and he didn't want to talk to them. So his library was 4 miles away. At the back of it, he had a big garden shed, which might seem like the size of my house. And in it, he had 2 lead balls, like this, suspended from the ceiling. Only this is not to scale. This is, lead balls. Now, the real problem is that he wanted to measure the attraction between 2 objects due to gravity. In other words, there's a gravitational attraction between you and me, or between me and this lead ball. So he had to be a long way away to look at the experiment, otherwise he'd interfere with it. So he had an aperture, a place where he could look through, and he put a telescope up there, and he stood outside in all weathers, and he was in his 60s doing this, staring through the window to take his measurements over a year. There's another set of lead balls inside there. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated. And then right in the middle there's a bit of glass, there's a mirror which should be suspended from a torsion wire. So you'd set it up like this in his shed, and you put it like that, and this lead ball would attract that lead ball, and this lead ball would attract this one, and so it would be pushed a little bit this way and twist the wire, and that would be pushed a little bit that way, and the wire would twist, and as the wire twists, the mirror which is dangling in there would twist it a little bit, and light which comes in would be reflected off at a slightly different angle, and all he had to do was measure the angle. He then had to move it the other way round Oh, he didn't move this bit. He moved the lead balls around so that you had an equal and opposite effect on the other side. So instead of having, you'd have that configuration. He had this is a very complicated technical thing for the time. 18th century we're talking about, and he put that way round, and then it was pushed the other way, and you could then see the displacement. Moreover, you could measure the period of oscillation of this, and from that get all the properties of the wire, the torsional constant. And that enabled him to measure big G, the gravitational constant, to an accuracy of 1%. And nobody improved on that for 100 years. He didn't describe it as that. He described it as though he was weighing the Earth. He was calculating the mass of the Earth, so that when you're attracted to the Earth through gravity, it's the product of the mass of the Earth, this big gravitational constant, divided by r squared, the radius of the Earth squared, which we normally know as acceleration due to gravity. And that quantity is essentially big G, and he measured it. And nobody could do a clever experiment. So he's a father of physics, experimental physics, some of the ideas of theoretical physics, and a lot of chemistry.
Okay, so I bet by now you want to know what this value for big G is. Well, in order to do that, you're going to have to download the Gravity Force Lab PhET simulation. It's on Moodle. Go do that now. Okay, so this is the simulation that you should have by now. Just a quick run through before I actually give you the task of what you want to do. Remember, we want to actually find the value for big G, the constant, universal gravitational constant. So straight from the offset here, you can see you've got the two masses, the blue one and the red one, and we can change the values of that mass to whatever we like. Alright, and for each of those. And as you change the mass, you can see that the force here between the two are changing. We can also change the physical distance between them, and then we can measure that distance. Note that this ruler is in meters. Alright, so that's 1 meter, 2 meter. It is probably the world's, well, I don't know if it is the world's biggest ruler, but it's a big ruler. And note that we measure from the center of each mass to the other mass, because remember right at the beginning we said it's the point masses that we are dealing with here. We measure the distance between the point masses. We treat the Earth as if it has no radius. All its mass is at the center of the object. So quickly again, there is the force. Here's the mass 1, mass 2, the distance between them. You should be able to, using the universal equation, be able to find the value of big G for different situations with different masses, different radiuses, and obviously they all have the same force shared between them. So let's go have a look at the next slide. So you know your way around the simulation now. What I'd like you to do is, if you have a look at the table, I've got two values in there. They don't have to be in there. Basically what I want you to do is to change the masses or the distance between them for 3 simulations. Measure the masses for each mass, measure the radius between each of them, and measure the force that they share. If you have all of that information, then calculate the value for G. Get 3 values for that and take an average of that. Do that now. Do it.
Seriously, do it. Do it. Do it.
So hopefully you have got an answer that is close to this. 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared. That is the value for big G. Hopefully you got there. If not, that is it. It's in your data booklet and you will be using it a lot. You'll be using it right now. What I'd like you to do is to use that information that we've just found to find the force between you and Yoda. So you'll need a little bit of information. Yoda has a mass of 0.150 kilograms. Well, you have a mass. You need to go and find that. The distance between you and Yoda right now, well, you need to use Google Maps to estimate that. I don't know where your house is. You know where your house is. I do know where Yoda is. Yoda is sat there. He's busy at Art Cafe having a coffee. So find the distance, estimate the distance between you and Yoda, your two masses, and find the force between the two of you. Do it.
Seriously, do it. Do it. Do it.
Right, so this is for myself. There's the equation, F equals gm1 m2 over r squared. Don't forget to square the distance. Here we go. There's my mass, 80 kilograms. Yoda's mass in kilograms. The distance between my house, which is a secret location and no one knows, is 13,378 meters from here to Art Cafe. And you plug it all in, and there we go. Force between me and Yoda, who's at Art Cafe, is 4.47 times 10 to the minus 18 newtons. Now you should note that that force is incredibly small, which is why we don't experience this or see the effects of it everywhere else. Remember, the reality is this, that all objects in the universe will attract all other objects in the universe with a force that is directly proportional to the masses and inversely proportional to the distance between them. Alright? Good. Let's come back to our gravitational field strength G. This is the same acceleration due to gravity that we've been dealing with the whole time during mechanics. The gravitational field strength at a certain point is the force per unit mass experienced by a small point mass placed at that point. Right. So we rearrange our equation there. By definition, we've just said it's the force per unit mass, which is given by that blue equation, and we know that our weight, which is a force, is equal to m times g. If we equate the Newton's equation, universal equation, and our weight on Earth, what happens there? Well, the masses will cancel, and we're left with g, acceleration due to gravity, is equal to the constant big G times the mass of, in this case, namely the Earth, divided by the squared distance between them. You should be able to know the unit. Unit is the acceleration due to gravity, so meters per second squared. We can use that information, if you have a look here, to actually find the mass of the Earth. If we know what g is, we know with the two constants of small g, big G, and the radius of Earth, we can rearrange that to find the mass of the Earth, and that's what we do. We find the mass of the Earth to be 6 times 10 to the 24 kilograms. So, the next thing. Remember, gravitational field strength is a vector. In the case of gravitational fields, it always points towards the object, the mass, and in this case it's the Earth. Now, just have a look at the diagrams on the right hand side here. There's two different bits of information there. Generally what we say is where the field lines are closer together, the gravitational field strength is stronger. So if you look at the picture on the right, the man standing by the two trees there, the field lines seem to be equidistant from each other, which would suggest that the gravitational field strength here on Earth is going to be the same. However, if we actually move out and change our perspective from space looking towards the Earth, you'll see that the field lines are no longer running parallel with each other, and they become a radial field. And what this suggests is that the field strength actually decreases the further we get from Earth. So in a radial field, G will vary. In a uniform field, G is constant. Okay, so what I'd like you to do now, these are some example questions and the tips. I'm going to zoom in on those, have a read through those questions, see how they solved, and have a look at the exam tips. That is the tip from the examiner who will set your exam. So take a close look. Okay, so let's tie this whole topic together now. We started off with circular motion. That was 6.1. We've now done 6.2, which comes to gravitation, and the two are obviously linked together when we consider, for instance, in the following diagram, the Moon in orbital motion around the Earth. We know from 6.1 circular motion that the centripetal force can be given by mv squared over r, and we know that the force shared between the Earth and the Moon in this case can be given by big G, the universal constant, the masses, and the squared distance between them. Since that force is the same, we can equate the two equations together, and once we cancel, rearrange, and if we rearrange for V, we can come up with this expression here, which would represent the speed in circular orbit. However, you should also remember from 6.1 that we can work out the speed using 2 pi r over t, which is also speed in circular orbit. If we square the 2 pi r over t and equate the two together and rearrange, we come up with this expression here. If we rearrange it for t squared, we have what we call an equation to work out the orbital period. Now, the significance here, if you remember, perhaps you don't, an astronomer called Kepler. One of Kepler's laws looks at the relationship there between the squared orbital period and the cube diameter or distance between the two objects. And it just so happens that that relationship is a direct proportion relationship as shown by that graph. Now, when you get back to school, we'll discuss that in a little bit more detail. What I'd like you to go on and do now, if you have a look at Moodle, there should be this activity here, where I'd like you to go and analyze data from the actual Apollo 11 mission to the moon to find gravitational field at different distances. So if you could do that, that would be great, and then you're done.
The Force will be with you, always.
True story, as long as you have mass. See you later.